Well, welcome everyone to Algebra 2, Section 3.4, Transformations of Functions and Graphs. For the warm-up, we're not going to do the first one because we didn't discuss that in the previous notes for 3.3 because we said, we're not going to do those. I want to say real quick before we get further into the notes, though, that I'm not feeling the best. So if I have to blow my nose at any point, I will let you know so you can mute the video so you don't have to hear me blow my nose. And then I'll scribble so that way you can see, hey, back, and check back in. All right, what does the word transform mean? Well, just general, normal, everyday use. It means that we're changing something, so it means to change. All real numbers except 6. What does it look like in interval notation? So we're starting off at negative infinity. We go all the way to 6, comma in between, and they're both parentheses because you don't get to either number. And then you also have, picks back up at 6 and goes forever to infinity. And it's everywhere in between, so you do a U. So you're not everywhere in between, but it's both of those. So you do the U for the union. So this and this. So now let's get into vocab. Transformation, that means to change. Once again, transform is to change. So transformation in math is going to be to change the graph of a function in size, shape, or orientation. That was really bad. I'm going to even redo those. Or orientation. A reflection is going to be to mirror the image over the line. For an example, y equals negative x. The negative sign tells us to reflect over the x-axis. So a reflection can be over any line. It doesn't necessarily have to be an axis, so an x or a y-axis, but it will most commonly be. And specifically, it'll most commonly be the x-axis. Now, keep in mind the x-axis runs this way, so a reflection could be like, hey, this graph, well, now it looks like this graph, and that should be the same, like left to right there. I messed up there. But it's just flipped over there. Next, for a scale change, check for a coefficient. Little note there. So like f of x is equal to sum a times x. Real quick on the reflection, the negative tells you if it's reflected. If it's not negative, it's not reflected. So stretch dilation, that's a more specific type of scale change. The stretch, let's go in orange, the function gets steeper. The points are further from the x-axis. So for an example, f of x equals 3x means a scale change by a factor of 3. And to note, a stretch dilation will always happen if your scale factor is something like a is bigger than 1, like 3 is bigger than 1, or if it's less than a -1. AKA if it's not between -1 and 1. So it's bigger than one of those. So like -3 would have also worked. A stretch can be thought of like think of like a rubber wristband or like a rubber band in general. A normal rubber band might look like that. But if you take it and pull both ends out, it might look more like this. And so what happens is it stretched up. So we can notice that it did get steeper, and if the x-axis is here, these points did get farther away at the top than they were before, because they're higher and lower than they were before. And then additionally, we can say that, hey, actually left-right though, what happened? Well, left-right, it got smaller than it was. It was wider on this one than it is over here. And that's because, well, in order to get bigger somewhere, it had to get smaller somewhere else for it to happen when you're just stretching it. Just like a rubber band or a rubber wristband, your bracelet. Compress. The function gets flatter, and the points are closer to the x-axis. So an example of that would be like f of x equals 1/2 of x. And in order to compress or shrink it, the scale factor a will have to be somewhere between -1 and 1. aka like 1/2 is between those two. It's a fraction or decimal that's smaller than 1. So if you take your same rubber wristband, and this time we're going to compress it down. So we're going to like squish it. Well, your new one is going to look a little bit more like this, to where it does get flatter, and if we make an x-axis, our points got much closer to it. And then we can also see, kind of like the stretch, excuse me, I was blanking on the word, as it got bigger one direction, it got smaller the other one. So as this one gets smaller up and down, it gets bigger left and right. So whenever we're talking about the stretch or compressor, we're talking about what it's doing up and down. Translation, and yes, the SL is capitalized on purpose because it's like a slide. And I capitalize those on purpose as well. So it's movement of the original function without changing the size, shape, or orientation. So an example would be like f of x is equal to x plus 2. Now, you might notice your first two, we had a negative in front of it, so that's multiplication. We had a 3 and a 1/2, so that's multiplication. This one, we're adding, okay, so we can add or subtract. So for a horizontal one, it'll be like in parentheses x minus h, some number h. For the vertical ones, because this is saying left, right, up, down. So vertical, up and down, it'll be no parentheses, y plus the k, so number k. And so it's always going to be plus or minus for the translation, whereas the other ones were multiply. A translation, another good way to think about it, is like you push the graph without moving anything other than it. So just like you maybe like push a desk in a room, or maybe like you cut and paste. I think most people, if not everyone's familiar with cut and paste. You don't change the look of it at all. You just change the location. That's all we're doing. All right, putting these into practice, using these words. The first one's done for us. We say from the black one or the purple one, the old to the new, what happened? Using our big fancy words we just learned, using reflect, stretch, compress, translate. So this one was translated. Specifically, it was translated right 2 units. We can see each time we can count 2 to the right from the original to our new one and find any point. So I want you to take pause and take a moment to figure out what the next 4 are as far as just what word it would be. And then once you have them or are stuck, continue the video. So the second one here would be a compression or a shrink. It's like you took it and pushed it down. Now, in order to figure out by how much, we want to take a look at these points, and we're saying, hey, we were worried about the y values, so it got flatter and closer to the x-axis. So it went from like -2 to -1, or 2 to 1, from old to new. Well, if we remember back to the previous slide here, compressing had some number multiplying with it. So we say, okay, what can multiply with maybe 2 to get 1, or -2 to get -1? And we'd say, oh, it was compression by 1/2, or by a factor of 1/2. You also could have said shrink as well. And it would have to be, by the way, the number somewhere between -1 and 1, which this is because it got smaller, shrunk. This next one, it was 2 different translations. So one, let's say the middle original to the bottom one, it went down. And it went down 3. The other one, the original to the top one, or like starting over, went up 4. The next one, this was a stretch. So went from -2 to -4, or +2 to +4 are some good examples. So 2 times what is 4? Well, a stretch by 2. And that would have to be bigger than 1 or smaller than -1. And then last but not least, this one was reflected. And specifically, it was over the x-axis. Means if you take a look at this x-axis, it directly flips. What's down here was up there. What's up here was down here. And it just keeps going every step of the way. Alright, so simple / sample transformations of functions and combination transformations. So it can have multiple of these transformations at once. So there will be times where, and quite often I might add, where not only will we stretch it by 2 or something like that, but we'll also translate, slide or shift, whatever word you want to use for that second one, by like down something and right something. That can happen all at the same time. So your base function is f of x is equal to a times parentheses x minus h plus k. And you notice A, H, and K all appeared from earlier. So A was with the scale factor. H was with the translation, specifically with horizontal. And K was with the translation, specifically with the vertical. So how do we know what they do? Well, this is a table to help you figure it out. So here's the first example. If the sign of A is positive, which it is, then it opens up. So this would be like the graph is a normal graph, is not reflected. And it is also stretched because the factor is bigger than 1. And then inside the parenthesis, the sign of H. It's positive, okay? That actually means to go left 2. But you might say, hey, Mr. Kossel, if it's positive, why isn't it going right? Because horizontal left is negative, right is positive. And that is accurate, that left is negative. However, you notice that this one is the only one that starts off as the opposite sign. That's because whatever's with the x inside the parenthesis, you always do the opposite. So when it says plus 2, think of it as, that's actually minus, so it's to the left. And then the sign of the K just tells you exactly what to do. So that's up. It's no tricky games there. It's just going at the end, plus 1 at the end, plus 1 at the end. So the up or down translations are always going to be at the end. The left and right are always going to be inside the parenthesis with the x. And the stretch and reflect are always going to be in front. So example 2, because the sign is negative, it will reflect or open down. So I'm going to say it reflects. The next thing, this says it translates. And for which direction? Well, it's right, left. And because it's positive, we're going to say actually it's the opposite. So left 4. And it also goes down 3. Next, this one, the first part, A, well, it's a positive one, so nothing. It doesn't reflect. It's a normal one. What's with the X? The H, it's a negative 5 we see. So that means it translates. In this case, we'll go right because you do the opposite of the sign you see. So the opposite of a negative is to the right for a horizontal, 5. In this case, we do exactly what you see for the Y, up 7. So only when you do the opposite for is what's with the X. Notice this one is also being squared. That doesn't affect the transformation as we write them at all. And the last one, we see a negative 1/2. So this one does a few different things. It reflects with a negative. The 1/2 tells us it's compressed because it's between -1 and 1 by 1/2, so compressed by 1/2. This -1 tells us it's translated, shifted, or slid. Right 1, because this -1, so you do the opposite. And this tells us -9, do exactly what it says, but down instead of left, right. So now, domain and range for these. How are these impacted? Well, sometimes they're impacted, sometimes they're not. So on these, we'll notice that they are going to be impacted. Excuse me. So on example 5, start with a function that has a domain -3, 2, and the range 1, 6 in brackets inclusive. and it's translated left 2 units and down 4 units. And we want to know what would the domain and range of the translation be, the new one. So after we change it. So we take this domain and we say, okay, domain, left and right. So for the domain, I probably care that it's going left 2 units. Do I care it's going down 4 for the domain? I really don't. So left 2 units, that means those x values are going to get lower, okay? So this isn't opposite stuff like we had up here. That's only for the actual equation. This is only for, this is for how it looks at the end, or how it affects the domain, the outcome of things here. So we're saying for the actual domain, instead of being negative 3 comma 2, we'll take those and we will subtract 2 because it's left 2. So it'll be negative 5 comma 0. And you do parentheses because there were parentheses before. For the range, you say range. Okay, we care that it's going down 4 units. We don't care it's going left right now because we're just talking about the up, down, the range. So it's down 4 units. That's minus 4 from the range. So instead of 1 comma 6, it's negative 3 comma 2. And because it started in brackets, it'll end in brackets. So this one affected the domain and range, as you can see here. Alright, example 6. Maybe try this one on your own. Pause it and come back. Alright, so domain of 1 comma 9, range negative 5 comma 4. For the domain, we care that it goes left 2. For the range, we care it goes down 4. So for the domain, left 2, subtract 2. So 1 minus 2 is negative 1. 9 minus 2 is 7. And it's started in brackets, it'll end in brackets. The range goes down 4 units, so that means minus 4. So negative 5 minus 4 is negative 9. Negative 4 minus 4 is negative 8. Started in brackets, it'll end in brackets. And that's your new domain and range. Alright, so now we're given a graph and we're asked to do this different transformation to it. So, translate it, this first graph, up 2 and right 3. So a good way to do it is pick a few points and move them. So in this case, up 2, right 3, we can count that. So pick a point, go up 2, go right 3, and say, hey, that's the new place for this point. Okay, and I'll even use a different color here to kind of highlight. So if I picked another point, I'm going to pick a new point by going up 2, right 3 from that, and saying, hey, that's where it actually lands now. Same thing for this, up 2, right 3, and my new point's right there. And we notice as we continue, it ends up being like this. And I could draw my arrows up higher to match if I wanted. I don't necessarily need to. At the end of the day, I took this graph and I translated it like it asked me to. It went up 2 and right 3 from where it was before. Example 8, compress the graph by 1/2 and reflect across the x-axis. So, reflecting across the x-axis, remember x-axis is this way. So what's up here will show up down here. And what's down here will show up here. So if we just reflected it, which we're not, it would look like this. Kind of. This second loop would be a little closer to there. But we're also having to compress it. So if you want, you could do a little sketch of what it would be and then compress that. Or you can do them at the same time mentally in your head. Either way will work just fine. So I'll do my new one in purple though, so that way we can see. So this, the highest point, because you got to pick a point, and at this point, if I multiply by 1/2, because compress and stretch are multiplication, it's not going to change anything. But if I multiply by 3, which is this point, 3 up by 1/2, I get 1.5. So that means instead of going 3 down at that left-right area, I go at that left-right, I'm going to go 1.5 down. And so I hit that and go to 0. Same thing over here. This was 3 down at that left, right. So the opposite of that is 1.5 at this left, right. And now I compressed it by 1/2 and reflected it over the x-axis. Oh, and by the way, I misspoke. The whatchamacallit, just the reflection, I would have had it right the first time. It would have looked more like that. All right.